All right, welcome to RAP Lecture 6, our second lecture of winter quarter, and a continuation into our discussion about digital communication, where we add even more non-idealities and things become even harder as we go from MATLAB simulation into thinking about how we want to make it implementable and realizable in the real world. We'll be talking about digital filters and synchronization. Digital filters, similar to the root raised cosine or the rectangular filter that we've already seen, we'll kind of be discussing how those are actually implemented on a microcontroller and thinking about how to realize them. And synchronization is a new topic we'll be introducing, and we'll be talking about some of the non-idealities that occur in the real world and how we can solve those. First,
some quick announcements before we get going. So I think Vaibhav and we've been working with teams over the past few weeks to get your schematics in order and implementing feedback from design reviews. So soon-ish here, we're going to release signups for the next stage of reviews, which are actually talking about PCB layout. But before you guys get to that, this weekend we're going to put together just a quick video sharing some tips and practical things we learned while we were doing our own layout and developing this project. So we'll share that with you guys, and then expectation from there will be watch that and then start working on board layout. For this lecture, unfortunately, we couldn't get an in-person room, but we anticipate being able to be back in person for starting next lecture. And lastly, a quick reminder, I know Vaibhav's pinged you guys about this before, but there's an IEEE census form, takes 30 seconds to fill out. It'd be really helpful if you guys could fill that out. It will be used to help IEEE apply for different things, just have some general stats about who our members are, what years and majors our projects are involved, people are involved in our projects. So with that said, let's get into this.
All right. So yeah, like I said, we'll be talking about two things today. Digital filters. So we'll be talking about two types: infinite impulse response and finite impulse response, what those two terms mean, and why for our project we'll be using one type of filter over the other. Then we'll be talking about synchronization and how we use that broad category of techniques to deal with noise, phase, and frequency offsets. And then towards the end of this lecture, but really more in our next lecture, when we start talking about sending packets of information, we'll be talking about timing offsets as well. So real quick, a recap of what we've seen so far. This is basically the plot that you should be seeing, give or take, by the end of assignment 4.5, or really assignment 5, because quote unquote assignment 4 was the designs. So we talked about how we generate symbols. We talked about the complex baseband notation that we developed to represent symbols. We talked about how you can then filter them with the root raised cosine, which is something we developed to get around the intersymbol interference using the Nyquist criteria for the same. You modulate them onto your transmission frequency and transmit, you receive, you demodulate, and then you interpret. All of this has been detailed in the assignment with some additional text to kind of fill in any gaps that we didn't cover as much in the lecture. Before we move on, any questions so far? Because unlike most of our lectures in fall, where we kind of brought it together at the end, winter will be very sequential, and each assignment will basically be add X to the previous code you've already written. Awesome. Really quick, I know that a few teams have reached out about different parts of the code they've been having trouble with. Sorry, it's been a bit of a busy week with midterms. I will start getting back to you over tonight and tomorrow.
All right, that said, let's talk about frequency versus impulse response. So there's kind of a design trade-off when you're creating filters. If you want a really sharp frequency response, like if you want a perfect low pass filter where it's like just a rectangle for the low frequencies, you can't have those infinitely sharp transitions, because when you go back to the time domain, the actual impulse response is going to be infinitely long and involve infinitely high frequencies. Or let's see. So there's kind of that trade-offs to deal with, and yeah, especially in the digital domain, which is what we're going to be working with going forward, implementing these filters on our microcontrollers. We can't implement an infinite impulse response by just storing filter coefficients, because that will require infinite memory, which we don't have. Go ahead, next slide, Vaibhav. Okay. Yeah. So an infinite impulse response, to put it very simply, is an impulse response that does not die out. However, typically a filter's impulse response will, at a certain point, it'll die down to a really low level, where it's basically going to be zero beyond that point. So just kind of a way around this to implement it on a microcontroller would be look at the important part of the impulse response, the part that's non-zero, and then after a certain point, just truncate it and say beyond this point it's going to be effectively zero, and stuff beyond this point won't significantly affect our signal. So there are ways to implement a effectively infinite impulse response on digital system. Usually that involves using feedback, but it can be, it's tricky to get that working and create a stable feedback configuration. So we're not going to use that so much here. Go ahead, Vaibhav.
Sweet. So that brings us to the finite impulse response then, which is basically the idea that beyond a point, the impulse response is zero. What that means is if you have something that's capital N, intervals or sampling points long, you can kind of write that as a summation of delta functions, and you can get the impulse response, or rather an input response, as that same delta chain multiplied by those coefficients. This means that at least when you compare the naive implementation of an IIR filter, you're only required to store the past n inputs and then the n+1 coefficients, the DC, the quote unquote DC coefficient, and then all your, well, not really, your time zero coefficient and your other delta coefficients. This FIR filters also have some other interesting properties that are useful for communication. If you actually plot out an FIR filter, they have linear phase they have a linear phase profile with frequency, and what that means is that the group delay in a communication system is it's more predictable. Basically, the phase of each frequency is impacted in the same way, whereas a analog filter will have non-linear phases. Anyone who's taken 115B, well, not A, but 115B might know, especially the back half of that course. So again, a lot of these details we won't really get into. It's just something to kind of keep in mind that, while for our system we're using FIR filters because they're easier to implement, it's not to say that FIR filters are better, period. Both of them have pros and cons, and are suited for different things. So generating FIR filters then is kind of along the lines of what Tyler already described. You take, some desirable filter that say the Chebyshev or the Butterworth filter if you're trying to design a low pass filter like we've discussed. You discretize it, that is, you sample it into an IIR filter, and then you truncate that within some acceptable time range. That is slightly hand wavy, and there might be some, accurate way of knowing exactly what is quote unquote acceptable. For the purposes of our project, we're kind of just doing try it at 30 samples, see if it works. If it does, try it again at 25. And if it doesn't, try it again at 35 until you reach that upper or lower bound of, hey, it works at this point. So you might have noticed that you already did something like this for the root raised cosine filters in the previous assignment, where what you did do, for example, is feed in the span and the symbols per second or samples per second rate into your MATLAB functions. Sorry, give me 1 second. There we go. Into your MATLAB function, and you would have seen that that generated a digital filter with a finite impulse response because you truncated it or cut it off beyond the point. Oh, before we move on to synchronization, any questions about infinite impulse response or finite impulse response filters?
If you could go back a few
How do you?
slides,
There we go. Yeah.
a little bit more, I think. Yes, this one. So, no, you passed it. Yeah. So why do we have only n inputs and n+1 coefficients? Shouldn't it be the same n+1 inputs?
Well, I say so it only requires you to store the past n inputs. Your nth input is just your current input.
Oh, I see. Okay. Yeah. All right, that makes sense. Just.
Okay. So we're going to switch gears a little bit here and talk about something called synchronization. So there's so if you just have two, if you build transmitter, build a receiver, and turn them on, there's nothing exactly guaranteeing that the transmitter, the oscillators on the transmitter are perfectly identical to those on the receiver. So the frequency might be slightly off between the two. And so previously we had you guys create a constellation diagram in this part of the assignment. So if over time the frequency is going to be higher or slower on one, so it's going to start rotating around, just form a circle. You don't have a constellation anymore. Let's see, there's phase offsets. There's noise that's interjected in the channel that is going to get picked up on the receiver. How do you define where the start of a packet is? If the transmitter just starts sending data, how does the receiver know which bits in that sequence are truly the start if it's always listening? Yeah, things like that. So let's talk about one of them. Let's talk about noise real quick. So this is the one thing we can't really account for. So we can model noise being added to our channel, generally just using Gaussian white noise, which means that it's going to be uniformly added across all frequencies that are transmitted. Let's see. Yeah, so I don't think there's much to say here. In MATLAB, we'll be having you guys kind of simulate this with by using Gaussian, introducing noise to your signal and modeling and seeing how many bit errors you'll come up with when you do so. Bob, do you have anything to add to this one?
No, not really. It's just that, like we discussed previously when we first introduced constellations, there is, a way to analytically describe what transmission power correlates to what acceptable noise you can still pick up, and what how many symbols you can realistically then still transmit, and other things like that. All of that is in EE 132A, which I would recommend is a great class to take if you're interested in digital communications. So let's talk about one of the impairments that we actually can do something about: frequency estimation. So to kind of expand on what might cause a frequency offset, right? Because so far we've said, even in the previous lecture, for example, that our frequency of transmission is known. And in fairness, it is known. Like, our entire design has been presupposed around the idea of 1 megahertz being up converted to 5, being up converted to 27, and then being down converted back to 1 megahertz. And all of that is fair. And in the MATLAB simulation as well, you kind of said, well, FC is 100 hertz. So what's the problem here? The problem is kind of what Tyler was hinting at. The microcontrollers have different oscillators that define what 100 hertz means. And so while 100 hertz might mean 100 hertz for one, on the other, the oscillator might drift by 0.1%, and now 100 hertz is actually 101. And what that causes then is, if you think back to how we defined the quadrature modulation and demodulation, where we were specifically the demodulation, where we were multiplying by cosine 2 pi fct or sine 2 pi fct, if you have a delta fc term there, then with time, your demodulated constellation kind of rotates throughout this scatter plot. Which is why it's important to estimate the frequency on the receiver end as well. That is, from our received signal that has some arbitrary phase shift and some, we have a rough idea what FC is, because, it probably won't have drifted by to have become double or anything, but we don't exactly know what it is. So we need to get FC and we need to get theta, but we'll deal with theta in just a second. We'll deal with the phase offset in a bit. So let's start by trying to estimate FC. So the way we do this for BPSK is we square our received signal. And when you do that, it's simply a plus b whole squared. So you get a squared, which is this term, plus b squared, plus 2ab, or in this case, minus 2ab. Now for BPSK, we already know that the in-phase term is either plus or minus 1, and the quadrature term is 0. We use those properties to then simplify y squared t to be simply this. And similar to what we did when we were first demodulating, we can express this in terms of the double frequency term. When you then find the FFT of y squared t, you will see two peaks, one at DC caused by this, and one at the double frequency term caused by this. And so because you have these two distinct peaks that lie above the rest of the signal, you can basically use this to estimate what your carrier frequency is. Now, as you might have noticed, we made one important assumption here, which is for BPSK. What that means is this method doesn't quite generalize as neatly as some of our previous discussions on constellations, right? The other things we've been discussing about how you modulate, demodulate, what the in-phase and quadrature term represent, they kind of stay the same for just about any modulation scheme you can choose, any encoding scheme. Once you start coming into some of this, it becomes a bit more specific. So if you had a more complicated, constellation diagram, you wouldn't be able to quite do this. You would have to use different methods to get to estimate the carrier frequency. Any questions about this? Sweet. So yeah, you receive some amount of data, you kind of do this, and that lets you estimate the carrier frequency. And using the corrected carrier frequency, you can then get these two noisy clusters that have some phase offset, which brings us to our next question, namely, how do we deal with this phase offset? So again, here we kind of rely on the fact that we know we're using BPSK. So the idea for any phase offset, really, because we know that our known constellation terms or our known symbols are going to lie on the real axis, is we can fit a line through the origin and our received data points to get this angle theta, and then rotate by negative theta. And the way you rotate a complex term by negative theta is to multiply it by e to the negative j theta. And so that's exactly what we do. We find this line of best fit, rotate back by theta, and now we have these clean clusters of plots that kind of line up well with our known formulation for BPSK. A second thing that we can do to make our lives slightly easier for BPSK is we can mirror one set of our data down to this second cluster. The way you do that is by taking one of the clouds and simply flipping them by 180 degrees. Any questions about this?
So how did knowing the carrier frequency help us to make the scatter plot this much organized?
Right. Okay. So think of it like this. So when we receive a y of t, which is I of t cosine 2 pi fc of t plus theta, right? If fc is fc plus some delta fc, then this becomes cosine 2 pi fct plus 2 pi delta fct, right? And what that means is your phase offset for that term is now a function of time, which means that if you receive, say, a 1 at time t at time t1, it might be over here, but at time t2, because of the delta fc, it might have rotated here, and so on and so forth. And so the problem with delta fc is, like, unlike theta, which for our purposes we can assume is roughly the same for any one packet of information, uh, delta fct would be a function of time. And so depending on when a particular bit of information came in, it would kind of rotate through this, because the corresponding demodulation would have the symbol rotating around the scatter plot with time. So basically what this has done is gotten rid of that part of um, that part of the non-ideality which was causing rotation in our constellation diagram.
I see. And the reason that right now the clouds are not exactly on the x-axis is because of that theta, which we are applying it. Like we want to have that theta in the transmitter, right?
No, it's not that we want to have theta in the transmitter. In fact, we already know that in the transmitter, theta is 0 because we know that it lies along the real axis. Theta is actually a function in part of our analog circuits. So for example, we know that common emitter amplifiers have a phase shift of 180 because they have negative gain. Similarly, if you look at your RF filters, if you go back to the website we used to design them, you'll notice that they have different phase responses. And so as a result of all our analog circuitry and then, additional, things that happen in the air, we get some theta offset.
I see. Okay. Yeah, that makes sense. Thank you.
Awesome. So yeah, we can estimate theta by using a line of best fit that goes to the origin. The way you do this in MATLAB is actually pretty straightforward. It's, a simple line of y is equal to mx plus b, but we know b is 0 because the line goes through the origin. So y is equal to, well, mx, and at that point it's simply a matrix division. Or yeah, you can use some matrix math to solve for m pretty trivially. So once you've corrected for rotating fc and for a phase offset, you get a scatter plot that has some amount of noise that is inherent to just communicating over air. But this is still something we can deal with. If we define our boundary at 0, as we did in this previous assignment, we can see that, hey, I can pretty reasonably guess everywhere where I transmitted a 0 and everywhere where I transmitted a 1. So basically, from something where I had just about no idea what was happening, I can now say with reasonable certainty that I've transmitted a 0 or a 1. So that's about all that we'll be discussing in this lecture and this coming assignment, which is the details of how to actually implement these things we've discussed. But this, and you may have started picking up on this stuff, this kind of isn't all that's important. So we talked about, hey, Um, we talked about, hey, there's some timing offset that might cause an error with the carrier frequency, but that kind of carries over to the symbol as well, right? Which is when we were talking about, a symbol starting and ending at a certain point, we assume that the two ends are sampling at the same points. If they no longer are, it becomes a bit harder to say where does one symbol start and where does the next symbol start. And without being able to do that, and even though we have a clearly defined symbol span, if both our microcontrollers aren't sampling at the same rates, or if we can't trust that they're sampling at the same rates, then we're no longer sure whether if, let's say, I send only one, but at the other end I read that as two ones before the next bit of information comes around. So we'll talk about how to deal with something like that. The second, though, is something you may have picked up when we were talking about phase rotation, which is, well, I kind of assumed theta was this offset from the real axis, but it could also be this offset. And how do I know whether it's this smaller offset or this larger offset? Because that basically will be the difference between this cloud being here versus this cloud being here, which means, do I read all my zeros as zeros or do I read all my zeros as ones? So how we deal with these sorts of non-idealities gets into basically the creation of data packets and adding packet headers, where we kind of send a known code, which is known to both the transmitter and receiver, to kind of get them to agree on some of these baseline terms before the actual information starts transmitting. Now, that raises more challenges of, well, hey, we've spent all this time saying that we don't know things that are needed to decode. So even if the code is known, how do I decode it if I don't know all of these things? So we'll talk more about packet synchronization and all of the challenges that we still have to resolve in the next lecture. And as you'll see, once you've implemented things like phase and frequency correction in MATLAB, you'll realize that not all of it as it's implemented in MATLAB maybe translates as easily into a microcontroller. So like we did the first time around, where we first had you use MATLAB functions for a low pass filter, and now we'll move to digital filters. Similarly, we'll first start by relying on MATLAB to develop an intuition for how phase and frequency correction work, before we then develop a discussion on how we would do that in the digital domain. Tyler, you want to?
Yes, sir. So I think this weekend we're gonna get to releasing assignment 6, which covers some things Byron just discussed. And also, like as mentioned at the very start, we'll start having signups for PCB layout review. And I know we haven't said, hey, start on your PCB layout. This is just giving you guys a lot of notice, like, hey, sign up for something in week 7 or 8, and then after that, start working on that in parallel with assignment 6 and whatnot. So that's all for today. Is there any questions above and beyond what's been asked so far?
Is there something for the PCB reviews that we should know before starting doing the layouts? Like, is there some kind of video you guys?
Yeah. Let's see. You kind of mentioned this at the very beginning, so sorry if you missed that.
No, I was there. Is it basically just about like trace thickness and your, what to do with your power signals and how thick those traces should be?
Yeah, we'll have some general guidelines, but also as a practical note, we want you guys to use the components that we already have. So like we have a certain footprints and available values for some passives like capacitors, resistors, inductors. So we want you guys to use those when possible. We have a specific connectors that you're going to be using to connect your antenna and stuff. So obviously you should use that footprint instead of us buying some special one, a different one for each team. And also, yeah, just stuff like that. So we'll kind of give you guys links to, hey, here's the libraries and things you should be using in your layout. There's some general guidelines. Have fun. So that'll kind of be what the video encompasses.
All right, sounds good. Thank you.
In the meanwhile, I would recommend, whatever software you're using, and fingers crossed it's Eagle, because that's for better or for worse, the one that most people in IEEE are, at least for now, most familiar with. I would say it's probably worth your while to try and translate your schematic from LT Spice into Eagle or whatever layout tool you're using. And really go through those schematics and make sure they're error free, because once you start laying out, the connections that the layout tool tells you to make is reliant on what you put into the schematic, and it is a pretty large schematic for both the transmitter and the receiver. So making sure that that doesn't have any errors in it and that you're actually hooking things up where they're supposed to go is probably an exercise worth doing as well. All right, with that, I'm going to stop recording if there's no more questions about what we discussed today.